let's start the second section. In this session, we are going to go a little bit deeper with the results that we have in classical mechanics for the reverse physics. And this is sort of the, let's say, the only theory where we did the whole approach, and all of the results are there in the book. For the other theories, we have a lot of ideas. For quantum mechanics, probably just a matter of putting them together. It's just that it will require time, and I haven't done it yet. So we are going to go and look at classical mechanics to just, again, give a sense of how the details are going to work here. Okay, so these are the four assumptions that we use for to recover classical mechanics. Infinitesimal reducibility, we briefly talked about it before. You have a system, and the system has an extension, is a finite system, and then you imagine that it can be broken up into little smaller and smaller pieces, and then studying the whole is equivalent to studying the part. We're not going to go through the details of much of that assumption, but it's always in the back of our head. The other idea is that the system is described by a series of independent degrees of freedom. And again, describing exactly what that means, it's a little bit, I mean, it requires some time, but basically this assumption of, I should say that the assumption of infinitesimal reducibility basically tells us that the classical state of a classical full system is a distribution over the state of the infinitesimal parts. And so the particles in quantum mechanics, you can think them as these infinitesimal pieces that we're decomposing the system in. Then, of course, they are going to become the center of mass for the position and momentum of center of mass for a class of systems that are rigid, that have particular properties. But in a most basic sense, that's what we get when we assume that we have infinitesimal reducibility. And we also get that the states are essentially point on a manifold, because we're assuming that the variables can be ranges that can become smaller and smaller and smaller, and therefore we're going to become real valued quantities. So the real valued quantities on the manifold you get from the assumption of infinitesimal reducibility. Then you have the assumption of independence of the degrees of freedom, which one might think that you already have in a manifold, because locally, it's the product of real line. But actually, from the physical perspective, the requirements of independence is stronger, because we have units. So if you define units on one quantity, then the other quantity can only be independent if the unit can be chosen independently. If it cannot, they're not independent. So if we have position and velocity, once we fix the unit of position, well, the unit of velocity is no longer independent from the unit of position. So they're not independent in a physical sense, not because you can't pick the two values that are different, but because when you define one, you have to define the other, or you can't define one without defining the other. We can't define velocity without defining position. It just doesn't work. And also, we need to be able to give account on these configurations. We need to have an entropy that it's invariant under changes of frame, because otherwise we wouldn't be able to talk about these descriptions as being really independent. They're independent because we don't care who is making the how you're describing it. And so there is a lot more physics that is actually like that you think that would be there in the assumption of independence of degree of freedom. And that's how you recover conjugate variables, where you cover the symplectic form and a lot of stuff like that. You recovered from this assumption of independence. Then you have the assumption of deterministic irreversibility, which we already talked about before, which can be formulated in different ways, that the entropy is conserved, the count of states is conserved, and so on. And if you take this assumption together with the first two, then you're going to recover Hamiltonian evolution. And then we also have this assumption of what we call kinematic equivalence. This is a little bit the trickiest one to understand. The idea is that the kinematics of the system, the trajectory is in space-time, are enough to reconstruct the dynamics. So we're going to have these two pictures of looking at things, a position and velocity and position and momentum, one just describe what we see, position and velocity in terms of some coordinates and how they evolve in time. And instead, the dynamics is going to be the momentum, the energy, the forces, the causes of motion. And we need a link to connect the two things. And this is what the kinematic equivalence does. And this is what allows us essentially to recover the notion of inertia, of masses, and of scalar and vector potential forces. And this is basically the picture that we have in our head, that if we assume infinitesimal reversibilities plus independence of the degree of freedom, we get the whole notion of classical mechanics. If we assume also deterministic and reversible evolution, you get Hamiltonian mechanics. If you assume that you have kinematic equivalence, you get Newtonian mechanics instead, and the intersection between the two is Lagrangian mechanics. And we leave the space out for statistical mechanics, where we where there is a lot more going on than just looking at trajectories, because of the trajectories so spread out in phase space. So these are the four assumptions, and this is how there you go. How basically they play around with each other. So as I said before, infinitesimal reducibility plus the independence of the degree of freedom, you're going to recover the notion of classical phase space. With classical phase space, adding deterministic and reversible evolution, you're going to get to Hamiltonian mechanics. Then you are going to add the kinematic equivalence. There are two ways to implement it mathematically. One is what I call weak, which basically just means that you have an invertible function between between momentum and velocity. And let me again get this pointer option fixed, because otherwise the cursor becomes invisible and it annoys me. And so if you assume that there is this way of recovering momentum from the velocity, you're going to be able to get to Lagrangian mechanics. The full way to implement this assumption is that since velocity is a linear under transformation of position, and so the momentum, they both have a linear structure. So the correct way is to link these two with a linear structure, because they're both linear structure on the same quantity. And that's basically meaning that you have a relationship between position and momentum, but that position is linear. And once you have that, you basically constrain the system to be one with massive particles under potential forces. And the metric tensor becomes that linear relationship between position and momentum. And now I'm losing voice, so I hope I will have voice for the rest of these 50 minutes. Okay, so again, in the spirit of we want to be able to have a lot of ways to look at things, just to let me, this is what we had before. This is what we had before. Also, the infinitesimal reducibility, there is a couple of ways to look at it. The kinematic equivalence, especially the full kinematic equivalence, has many equivalent ways to look at it that are very interesting, that they are equivalent. And it's probably even an area where probably even more work can be done, because I still have not gotten over it of how some things are surprising. So as I said, it's basically assuming that there is a linear relationship between conjugate momentum and velocity. And then assuming this is essentially assuming that there you have massive particles under scalar and vector potential forces. So the fact that these two things are the same, and this mathematically you can show very easily, is kind of mind-boggling. And but there are other things that are sort of similar, that are sort of surprising, that if you're at each position, you assume that there is a local inertial frame, then that's the same assumption. Or that the position fully defines the units of all state variables, and therefore an inversible transformation between momentum and velocity, then again you get the same thing, which again is surprising. So we're not going to look at that too much. What we're going to look at is the action principle. And I'm really losing my voice now. This is not good. Okay, so I'll try lowering my voice. I don't know if I'm going to hold. Well, Okay, so the required background to look at the action principle is that we're going to have some equations from Hamiltonian mechanics, which are the usual one. Hopefully you're familiar with them. From Lagrangian mechanics, we use the notion that the action is the integral of the Lagrangian over a given path. So we have a path gamma over position, and we are going to have an action. It's going to be the integral of the Lagrangian, which is a function of position and velocity and time. The actual evolution are the paths that take the action and make it stationary. So the variation of the action is zero if we vary the path. And the Lagrangian is the Legendre transformation of the Hamiltonian. So Lagrangian is position times velocity minus the Hamiltonian. We are going to use some vector calculus ideas, because what we basically show is that the principle of stationary action is just an application of vector calculus. Given a vector field V, a field line is a line that is always tangent to the field. Given a vector field V, we have a divergence that gives us the flow of the field through an infinitesimal closed region. And the divergence-free field, a divergence-free field is a field for which the divergence is always zero, admits a vector potential A, such that B is the kernel of A. So this is what we have for a magnetic field, for example. It's going to be the same thing that we're going to have for the action principle. So the first thing that we should say is that when somebody is introduced with the Lagrangian, is told that the Lagrangian is the difference between a kinetic energy and a potential energy, and this does not always work. So this is the Lagrangian for a charged particle in an electromagnetic field. This is the kinetic energy. This is the potential energy. This part is neither kinetic nor potential. If we go to field theory, you're going to have mass terms and interaction terms. Are those potential or kinetic? It's all this idea is sort of ill-defined. That's what should tell you that if you want to really understand this action principle, you have to abandon this simple idea and find something that works more in general. So what is the correct setting to understand this the action principle? Is going to be in what is called the extended phase space. So we have position and momentum here. So in this plane, we have all the states. And then we have here time. And so states are going to be flowing in time. And at each point, we are going to have what we call a displacement field that is going to tell us how we're going to be evolving time. It's telling us how we move into time. These gammas here are the actual evolutions, and the actual evolution of the system, you can imagine them as being position and momentum and time as a function of time. And what is important here is that time plays two roles. First, it can be the affine parameters on the curve. So it tells us how far we are on the curve. So when we are changing this time, we are going along the curve. Or t can be a variable. So if we're changing t itself, we're just going along one of the axes. And this is important because a total derivative is meant to be a derivative in time over the evolution over a path, while a partial derivative in time is meant to be a derivative at t with p and q constant. So those are two different things. But the thing that is important here is that the evolutions are field lines, and so they're always tangent to the field. That's the important thing. Now we're going to add the assumption of deterministic and reversibility, which here is implemented by just saying that if you have a closed region, we have a potato, then as many states flow in and as many states flow out. So the surface integral through that closed surface is going to be zero, which means we're going to have a divergence-free field. Now, if we have a divergence-free field, as we said before, it emits a potential. This theta is going to be our vector potential, and we're going to stick a minus sign in front of it to match the convention that we have in classical mechanics. Once we have that, we can say, okay, how can we characterize this vector potential? Well, it's a vector potential, so it has a gauge. We can use fix the gauge to make our vector potential look nicer. And the way that we're going to fix the gauge is to take this component and set it to zero by making this transformation. Then another thing that we can do is calculate the component st, which is going to be partial p theta q minus partial q theta p. And this has to be equal to dt dt. But what needs to happen is that dt dt is going to have to be equal to 1. So we want this component to be 1. Now, theta p here is 0, so we don't have this part. So we just have that the partial p of theta q is equal to 1. So without loss of generality, we can just set this theta q to p. And so now our vector potential is p, 0, theta t. These are the components. And this is an arbitrary function. And we can just rename this to minus h for no apparent reason. And so without loss of generality, under the idea that we have 1 degree of freedom and we have a deterministic reversible evolution, we can say that the displacement field is minus the curl of the vector potential, and the vector potential has component p, 0, and minus h, where minus h is an arbitrary function of position of momentum and time. Once we have that, we can say, okay, let's go and actually calculate this curl of this theta. And if you do the calculation, what you find is you recover Hamilton's equation. For example, theta t here is minus h. So you have minus the partial p of h, but you have another minus here. So you get the same thing. Theta p is 0, and this goes away. So you get the same thing. So what we already have derived, just by this simple assumption, we recovered Hamiltonian mechanics with 1 degree of freedom by saying that we have deterministic and reversible evolution. Good. Now we have this vector potential. What do we do with this vector potential? Well, it's a field. We can define a line integral. Why not? So we take a random path gamma that is not necessarily an evolution, but we still want it to go forward in time. We don't want it to go back because those evolutions do not make sense and we wouldn't be able to parameterize them with the time. Okay, so these are the components of theta, p, 0, minus h. And the gamma, like this, the infinitesimal displacement over gamma, can be written as dq dt, dp dt, dt dt, multiplied by dt. And now we have just the scalar product. So we have p dq dt, so it's momentum times the velocity, 0, so it's going to be 0, and minus h times dt dt, which is 1, so we have minus h. And you can recognize that this is pv minus h. This is a Lagrangian, except that we have to assume that we can expect that we can express this p in terms of position, velocity, and momentum. This is where the kinematic equivalence assumption comes in. Otherwise, we would have a Lagrangian with a function, but it's not a Lagrangian because it would be a function of position, velocity, momentum, and time. Now, because we have key, we can explicitly write it is in terms of velocity. And now this is the action. So what we see is that the action is the line integral of the vector potential of the flow state. So we know what the action is. It's a line integral of the vector potential. The vector potential is unphysical because we have fixed the gauge. We could change the gauge. We can do different things. That's why the Lagrangian is not unique. And that's why the action itself tells you nothing. The action, you don't go and measure the action. Like there is no physical meaning. If I have a path, the action is 5. What does that tell you? It tells you nothing. So now we want to understand what is the variation of the action. And what we can look at is we have a path, we have a variation, and we're going to have some flow that goes through the surface that is in between the path and the variation. So we have the flow, and we define it as minus the integral of s with respect to the surface. Now, S, we saw before, minus S is the curl of theta. So using the Hamilton equation, we can make this step. We put it here. But this is the surface integral of the curl. We can use the Stokes theorem. And now it becomes a line integral on the contour of theta. So it's the line integral of theta along this line and along this line. Now, note that we're taking this line in reverse. So it's going to be the integral of over gamma minus the integral over gamma prime. This is the variation of the action between the path and the variation. So this is the variation of the line integral of the vector potential. This is the action. So this is the variation of the action. So the variation of the action geometrically tells us what is the flow of states through a path and its variation. And that is physically meaningful, because how many states go there, what the flow is, that's telling you how the system is evolved. It's characterizing how the system behaves. So this is the interesting bit, is that the action itself isn't physical because it comes from a vector potential, but the variation of the action, because we're doing the Stokes theorem, becomes something meaningful and geometrically interesting. Okay, so now why does the variation of the action, why is the variation of the action 0 along an evolution? Well, suppose that gamma is an evolution, right? And now what happens is that gamma is a field line of the displacement field, so it's always tangent to gamma. If our variation is small, right, then this infinitesimal surface will also be tangent to the flow. And so there's not going to be any flow that goes through the surface between the path and variation, and therefore the flow is going to be 0. So if I have a path and I make a variation of the action, then I look at the flow is going to be 0 because the field line is tangent to the flow. Conversely, if I have a path and the path is not an evolution of the system, then I can always find some variation that catches the flow. So if my path was like this, I make a variation on this side, we're going to catch some flow. If I catch some flow, then the variation of the action would not be 0. And the path would not make the action stationary. So the stationary the action is stationary over and only over the evolution, precisely because the evolution are always tangent to the flow, and the variation of the action measures the flow through the path and the variation. And if the flow is tangent, then there is no flow. And those are the only lines that have that. So what is beautiful to me is that something that is absolutely mysterious, that is said when you do physics, you don't know where this comes from, is justified by things like that nature is economical or some other stuff like that. Actually, it's a very, very simple geometrical representation that only requires vector calculus, which is something that in physics and engineering and so on, you need to do E&M. So there is nothing extra. So this is, where is it? Okay, this is how it works. You assume that you have 1 degree of freedom of classical space, you have deterministic irreversibility, you have kinematic equivalence, you get the principle of stationary action. But the thing that is even more interesting to me, if we remove this kinematic equivalence, right, we are still going to have a pseudo-Lagrangian. It's just not going to be a function of just position and velocity and time, but there's going to be position, velocity, and momentum and time. And so this interpretation of the action principle actually still works, and you still have some type of action defined, which tells you that really to understand the action principle, the action principle is really a property more fundamentally of Hamiltonian mechanics than of Lagrangian mechanics. And Lagrangian mechanics just makes it more specific for some cases where you have this kinematic equivalence, and so you can express the momentum in terms of the velocity. So to really understand things, even in Lagrangian mechanics, you should really understand Hamiltonian mechanics and the notion of phase space. Okay, so this is for 1 degree of freedom. I want to go through a little bit more quickly on the multiple degrees of freedom, because it's nice to understand how things generalize, and it's also nice to see how the math works, and it sort of gives you a sense of something that we're going to be talking in other presentations, that sometimes the math that we have given by the mathematician, in this case differential geometry, it's not quite spelled out in the way that we would need it to understand the physics. And it is possible to sort of reshuffle things around so that the physics is more brought up. So I'm going to show you sort of how I think of the differential geometry and the notation that I use, that it's much similar way of the Einstein component notation that we typically use in general relativity. And I think sort of gives you a flavor of what is required to sort of make these insights more general and more precise. So here we will need some elements of differential geometry. If you have done a special general relativity, it would help because you will be familiar at least with some of this notation. And if you don't, I'll just try to give you a sort of a high-level understanding of what these pieces are. So in differential geometry, you have something called a differential form. So a differential n form is something that takes n vectors. It's a function. I give you some vectors, and it returns a number that depends on the volume that those vector or the parallelepiped that those vectors make. So, for example, you can imagine that I have work. Work takes a line, right? I have a path, and it tells you what is the work that I need to take from taking the particle from one side to the other. And we can think that as the integral of the path of infinitesimal contribution of work. And this is the number that we want, this infinitesimal contribution. And this can be seen as a force applied to an infinitesimal displacement. So this infinitesimal displacement is the vector that we're giving to the force. And the force is a function that takes a vector and it gives us the little amount of work, the infinitesimal amount of work that we need to sum up. Now, F now is a one form because it's taking a vector and it gives us a number. Now, if you study differential geometry, you will see that typically these dx's are the basis of the one form. I'm not doing any of that. This is the standard way that you do. It's much more closely of what we do in again, in vector calculus. So these displacements are vectors, and we can give vectors to functions of vectors, which are the forms, and we get numbers. Same things, you can imagine a magnetic flux. A magnetic flux takes a surface, and you want to know what is the flux that goes through. Well, that's going to be a surface integral of some infinitesimal contribution. And the infinitesimal contribution are going to be given by the magnetic field and the two vectors that give you the infinitesimal area element. And again, what I'd like you to think about is magnetic field not as the vector that is perpendicular to the area element, but as a function that takes the two direction of the area elements, the two vectors that make the area dimension, and give you a number. Why you should think like this? Because this is the way that things generalize. Even when you are in special relativity, you think as the electromagnetic field as a rank 2 tensor. This is what you're doing. You're giving it two vectors and it gives you a flux or it gives you something else. Right? This is how it works. And same thing, if you have a mass, if you have a volume, you can say how much mass there is inside there. That's going to be a volume integral of the infinitesimal contribution of mass. And that's going to give you by a mass density times the volume of given by three vectors. So again, I encourage you to think as a mass density as a function that takes three infinitesimal displacement, three vectors, and it gives you the infinitesimal mass. Once you think it like this, you can see the pattern, and now the pattern works in any generality of any surface on any dimension. So you have an n-dimensional space. You have an integral of a function that is defined on an m-dimensional surface, and you can think that as made of infinitesimal contribution of an m form over m vectors. So pseudo-vectors are really two forms. That's how you should think about it. I kind of wish that even when we did vector calculus, we did it in this notation with this idea, because these are the things that generalize, so it makes it easier for later. But there are some advantages when you're only stuck in three dimensions with vector calculus. But then there is the notion of an exterior derivative that is basically a generalization of the gradient and the divergence of the curve. And it can be defined on, for example, on a simple scalar function. And this basically is the gradient. It can be defined on a single one form, and it gives you a two form, which is the curve. Then it can be defined on a two form, and then that's going to give the divergence. So if this were the magnetic field, then this would be the divergence of the magnetic field, and this would be 0, right? And we're writing the magnetic field with this different notation. Once you have internalize this, and of course you're not going to be able to internalize it in the 2 minutes that I'm explaining these things, you have generalized properties. So you have a generalized Stokes theorem that whenever you have an integral of an exterior derivative of something, then you can take this integral and make it on the boundary. For us, it's still going to be a vector potential, so it's not going to, you don't have to understand the general case, but the important thing that this works. And also what gets generalized, if I have a 2 form, that it's an exterior derivative is 0, which means it's the divergence is 0, then it admits a vector potential. So the point of doing all this is to be able to say the same thing that we had, that we have a 2 form, in this case was the flow, it has a divergence, some type of divergence 0, then it admits a vector potential. So that's what the math that we have here allows us to do. And so the way that this generalizes is now we don't just have a Q and a P here, we have all the possible degrees of freedom, and again we have a flow in time. And then we're again measuring the flow, but we're measuring the flow still on area, not on volumes, because we want the flow of a configuration of each degree of freedom. That's what we are going to want to characterize. And so it's a function of 2 vectors, because we're still going to characterize areas in terms of 2 vectors. And we want to, whenever we have 2 things, 2 vectors, we want to say, okay, how much flow do I have through a surface that it's made by the student infinitesimal vector. So we can do that. And what we find is that if you assume deterministic irreversible evolution, we kind of have a sort of a divergent-like thing on time, meaning that the configuration are conserved through time. So if we make this variation of the flow along time, we need to have a 0. And this captures the assumption of thermic reversibility. For the independence of the degree of freedom, the configurations are conserved across degree of freedom. So if I have a little bit of an area that is defined on a degree of freedom and make a modification, then those configuration has to be the same whether I shift over an independent degree of freedom. And this means that now the partial, these derivatives in terms of positional momentum also are going to give me are going to be 0. What is interesting me mathematically is that if now we have both these conditions, we have this idea that the form is closed and therefore it will emit a vector potential. But you see that, well, mathematically, this is a nice and compact single requirement that you're making. You're making 2 different mathematical requirements in terms of the physics. So if you fail, for example, to be deterministic, but you still have this degree of freedom, there are some things that are going to survive while the other one does not. So this is exactly the thing that you have to do in reverse physics, is understanding exactly how the physical assumption map to the math, and sometimes it's not a neat map one-to-one, because it isn't. There is no reason why it has to be always at the same time. So this is why I wanted to look at to show you the details of multiple degrees of freedom, because you can see that there are things that are sometimes not nice, and then you have to be able to understand it and deal with it. But now, once we have this assumption, then we can basically go and say essentially what we did before. This form is closed, it will emit a vector potential. And then, again, without loss of generality, you're going to be able to see that this vector potential has the P, the sort of corresponded conjugate momentum in the position. So these are n components of position, and they're going to be the n momenta. Here is 0. These are the component of momenta that are all 0, and the time component of the vector potential is T minus h. So this, if you studied again relativity, this is basically the form momentum, right? These are the components of momentum, and this is minus the energy. There's just no C here, but it's basically the same thing. Now, if you do the calculation, and I'm not going to do that, you find that omega can be expressed now in terms of h. This is basically so this is a symplectic form. It's a 0 identity minus identity 0. If you have studied some symplectic mechanics, you recognize it, but then there are the time components. The time components are given by the entropy. So the mathematical formation is a little bit different. Now we have to sort of relate the flow with this so the displacement field with the flow, right? So before, in 3 dimensions, the flow and the displacement field were essentially the same thing. We were doing a surface integral of the displacement field, which was also the flow. Here, the flow is sort of a one-dimensional vector field, while this the displacement is still a one-dimensional vector field, but the flow is a two-form. So the relationship that you need to have between the flow and the displacement field is that if we're taking the flow and one of the vector that we're giving to calculate the flow is the displacement field, then the flow has to be zero because the flow because the displacement field has to be tangent to the displacement field has to be tangent to the flow. It has to contribute no flow, right? And so for whatever W that we put here, when we go and calculate the flow from a surface where we're going across the path, this has to be zero, which means that if for every WB, this has to be zero, then this has to be zero. Like the constraint that we're making, the relationship between the flow omega and the displacement field S is that if we take this and contract with the first index, then we need to have a zero. But since there is a B that is free here, we are going to have a 2n plus 1 constraint. So this is actually giving us 2n plus 1 constraint. And if you make the calculations, what those constraints become, they're going to become Hamilton's equation. So again, in sort of a similar way, we have used the deterministic and reversible evolution and independence of the degree of freedom, and we have recovered Hamilton's equation. And once we have, again, these relationship, we can go, we have a vector potential, we can define the integral of the vector potential, and the integral of the vector potential, again, we're going to find that it's the action. So the action is, again, the line of the potential of the vector potential of the flow. And then, again, we are going to calculate the variation of the action, and we're going to find that the variation of the action is actually the flow between the trajectory and between a path and its variation. And the variation of the action are going to be is going to be zero if and only if we have a path that it's always tangent to the flow. Because if we want this to be zero, then this has to be zero for every variation, which means for every one of these. But now what we're going to have is that if this part here has to be zero, no matter what this is, then this part here has to be zero. So we have to, this has to be zero. But the only direction that kills the flow, that for which this equation is valid, is the actual evolution. So you can recover all of that. So again, the important bit here is that the math becomes more complicated, but the physics does not. The sort of the conceptual parts are still the same. It just becomes a little bit more difficult to map the physics to the math because the math is more advanced. You need to know the more advanced math, but there is a way to look at the advanced math in a way that it's physically meaningful. And a lot of the time, when you just open up a math book, the way that things are set up, they're not there to give you a picture that it's useful for physics. It's a picture that it's useful for mathematicians to think about the problem, calculate, and prove theorems. And that's not always the way that we would like in physics. We would like to have definitions that are mapped closely to what we would like. Okay, so this is as much as I wanted to show. And again, if in any of these things, if there are people that want to dig more deeper, we can, if anybody wants, we can set up another live and we can go through more of these. And this is, again, it's all in the book. And everything that it's interesting for me to talk about and discuss quickly, because we don't have a lot of time, it's a connection to relativity. Already we saw that the theta is very close to the form momentum, essentially. So we already are seeing some elements of relativity appearing out of nowhere. The energy is the time component of a covector, right? So we didn't assume anything about speed of light or anything. So what I wanted to show is that there are some elements of relativity that essentially appear out of nowhere. And because, again, the laws and these assumptions constrain the law a lot more than you would expect at the beginning. And this is part of the fun in reverse physics, in realizing that the physical problem is a lot more constrained than we think it is. And so these are the things that I will use from relativity. We are going to have space and time coordinates, and they're grouped together. And typically you group them with the time rescaled by the speed of light. So this is units of distance, and then you have the position. There is a metric tensor that defines the geometry of space-time. Again, I want you to think as a tensor as a function of two infinitesimal displacements. So a metric tensor takes two infinitesimal displacement, and it gives you the length of the two times the cosine of the angle between them. That's what it does. We are using the minus plus plus notation because it's the one that physically maps better to the thing that we do. So the unit distance defined by our metric tensor is going to be dx squared plus dy squared plus d3 squared minus dt squared, at least locally. And then we're going to have an energy and momentum, and these are grouped together in the form momentum. So we have minus the energy over c and the pi. So again, note that this c here is because there is a c here. If we define this as a t without the c, this would just be minus e, and so it would be even more similar to what we were doing before. But you know, it's just a matter of how convention of the units, how you want to define things. The other thing that you have in relativity, hopefully you know, you have a forward velocity, and the forward velocity is velocity with respect to proper time, which is the time in the rest frame, and we use tau to calculate it. And because we're using the minus plus 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 signature, the norm of a forward velocity is minus c squared. So u alpha is going to be our forward velocity, which is derivative with respect to proper time of the position and the time. And the norm of the forward velocity is going to be minus c squared. And for a free particle, you have the relationship between the forward momentum and the forward velocity, which is the forward momentum contracted by with the metric tensor is going to give you the upper version of the forward velocity, which is basically in our case just changing this minus e into a plus e, and this is going to be the mass times the forward velocity. So these are the pieces that we need from relativity, which of course, if you haven't seen them, you're not going to learn from now, but at least you know that you don't know them because you don't have the background. Okay, so let's say that we want to extend Hamiltonian mechanics to handle change of coordinates that mix time and space. Okay, that's what we want to do. Then, of course, our position now we need to include the t and qi, right? And an evolution on t on an evolution instead of describing as t, like we do not want t to be the parameter of the evolution anymore, because we don't want it to be special. Then we are going to have an affine parameter, right? So we separate the time the variable from time the parameter, and now the parameter is going to be s. So when we're going to make a change of coordinates, we're going to change this t, and we're going to mix it with this q, but the parameters remain the same. And the parameter is an absolutely unphysical quantity that we could rescale however we want. It's just a dummy variable that we use. Right? It doesn't have any particular physical meaning unless we pick a particular meaning. So in every frame, we could choose s to be t, right? But when we change a variable, we keep s the same. So otherwise, we just make a mess. Now recall, now we are going to need the coordinate, the conjugates of t and qi. And we know that the conjugate of q are the p's, But the question is, what is the conjugate of t? Like, how do we find it? Well, we saw before that when we had our vector potential, P was here, and minus h was the time component of the covector. So we know already that the minus h is a time component of the covector, and during coordinate transformation, this is going to mix with these exactly like the time component of a covector that it's only defined on positioning momentum. So we only have one way to fix the conjugate. The conjugate has to be minus e, because otherwise when we make a transformation of this, it's not going to be matched by a transformation of this, and we're not going to preserve the fact that deterministic irreversible evolution is the same in all frames. It just becomes a mess. So you need this, and now what you can write is the Hamiltonian mechanics on the phase space extended both by time and energy, right? So you have 4 variables now, t, qi, e, and p. You have what is called a Hamiltonian constraint, which you can use to create, to write the laws of evolution, but it's also a constraint. It's not a conserved quantity like the Hamiltonian, that it's something that you can set it whatever you want at the beginning and it just gets conserved. No, this has to be the same value for everything, because what's going to do by being a constraint is going to be able to fix the relationship between energy and all the other variables. So the Hamiltonian, the standard Hamiltonian that tells you how things evolve in time is essentially hidden in this constraint. And what's nice about this constraint is that now it's invariant. And one of the reasons why you prefer Lagrangian mechanics in a relativistic framework is because the Lagrangian is invariant and the Hamiltonian is not. But if you use this constraint, now this is invariant, and you can start thinking about symmetries in terms of Hamiltonian mechanics instead of Lagrangian mechanics. So it has a nice features to it. Okay, so one of the things that this explains is already, we see that there is this minus sign that comes in from the degree of freedom in position and the degree of freedom in momentum. And the way that I think about it, this is again, position, the 2 different degrees of freedom are orthogonal because they implemented at different states. They are independent degrees of freedom, and therefore I have a plus sign between these 2, right? So it's like as if I had a Pythagorean triangle, right? These things are orthogonal, meaning they're independent. And then if I have a surface that sort of span the 2 surfaces, I just using the Pythagoras triangle and get the sum of the 2 areas. Now, what happens is, why do I have a minus here? Well, if I have a minus here and I want to still think about my Pythagoras triangle, what I just need to do is take this and bring it on the other side. And what this is telling me, which is of course very true, is that state must be defined at equal time. So it is not, if I have a region, like if I have an interval of position, that's going to define different types of initial condition, different type of configuration, different types of like a number of states. But if I have an interval of time, I'm not creating more states in time. Like it's always the same states that are evolving. So the form that sort of measures the flow, that measures the configuration, that defines the configuration and counts the state, has to be orthogonal to the temporal degree of freedom. And so now we still have a Pythagoras diagram, but the omega, the thing that counts the state, is not the hypothesis anymore. It's one of the sides, because it has to be perpendicular to the temporal degree of freedom. And again, this way of looking at this is a lot more geometrical, a lot more physically intuitive, and it's telling you what's actually going on in physics. It's not just a minus sign, because it's telling you something. And I'm sure that there are a lot more things that can actually be derived from this in a much more sensible way in things that we are looking at relativity. But one of the things that is clear here is that all of this reasoning comes because we're working in phase space, not just in space-time. And so I'm not going to be able to have the time to go through it, but what really seems to be the case is that this this signature space-time, it's actually something that it's inherited from state spaces. So at least when you're doing mechanics, the state spaces are more important than, say, the geometry of space-time, because you can recover the geometry of space-time from the geometry of phase space, but you can't do the opposite. So we're starting to run out of time. So I think I'll have to just flash these slides just to see, to show you how nice this old math is. So this is the free particle with an inertial frame, and you see that this is nice and quadratic, and it gives you the correct equation that you would expect. This would be the standard way that you do Hamiltonian mechanics in relativity, and it connects to this Hamiltonian mechanics in the extended phase space. It's just that this is much nicer to work with. Another thing that comes out of the blue is this notion that you can have classical antiparticles. So you typically think of antiparticles being something that you need a quantum field theory for them. And what happens instead here, very simply, is that we have a quadratic term for the energy. So the energy could be both positive and negative. And from the equation, this could be negative. So and the parameterization goes backwards in time. So our displacement field in terms of parameterization goes forward in time for some state and goes backwards in time for some space. You might have heard sometimes, oh, antiparticles are like particles that are going backwards in time. They're not going backwards in time. It's just the parameterization that one would use is opposite with respect to time. And of course, there is since the parameterization is unphysical, you can change what is a particle from an antiparticle just by changing the sign of the parameterization. It doesn't really matter. But again, what is interesting to me is that you can find these relationships in just classical mechanics, classical particle mechanics. Then if you understand them here, you're going to have a much easier time to understand them in field theory and so on. So this is, again, what I want to stress is that a lot of people that look for new theories and so on and say, who cares about classical mechanics? I just want to do my quantum gravity stuff. There is a lot of insight that you can get just by looking at these simpler theory. And it's much simpler to understand things in a simple theory than one so complicated like quantum field theory. So if you get good intuition, perfect intuition in these cases, and you know what carries out, because some of the assumptions are going to be the same, it's just going to make your life easier. And this is how you would recover a standard Hamiltonian. We are not going to have time to look at this, not time to have a look at this either. And so basically, what is important to me is that relativistic mechanics is recovered without any additional assumption. So relativity is basically needed to make density and entropy invariant over time transformation. That's what happened. In fact, I think there should be a very trimmed down version of these arguments where you can really say, okay, I have the probability distribution and they need to satisfy this requirement under covariant transformation, and then you're going to get a metric tensor. I still don't know how to do it technically, but I still think that there should be, this is very, very simple. That doesn't even require all the phase space. Like it's going to be much simpler. Then again, if you have never seen the Hamiltonian mechanics of the extended space is really a more relativistic formulation. It's kind of sad that it's not more popular, because it's something that even in field theories you can do, and it's been known since the 40s that you can do this. It's just not popular. I don't know why. And again, you can also make some connection of quantum mechanics, but we haven't seen them. I had a whole other section on the directional degree of freedom. I'm not going to have time for that, otherwise there's not going to be time for question. But really, what is important here is that we have done a great deal of work on classical mechanics to understand all these pieces. I consider the reverse physics part of quantum classical mechanics essentially done. I'm sure that it can be done better. As I mentioned before, there was somebody who approached me to extend the action principle to to dissipative systems, to put in the Riemann dissipative functions and stuff like that. I'm sure that can be done. That there could be the link to Newtonian mechanics probably could be done more precisely, but I don't think any of these things will require any new assumption or a new concept. The assumptions that we need are those four: infinitesimal reducibility, independence of degree of freedom, determinism reversibility, and kinematic equivalence. And again, I personally feel, and all the people that I talk to sort of confirm my feeling, these are assumptions that are understandable at a physical level. They don't feel like very mathematically heavy, and they're conceptually simple. And the fact that you can have multiple ways of implementing these assumptions it allows you to get more insight that you can reuse. And so the point is that all the classical mechanics are consequence of those. And so a lot of the physical ideas that we have in classical mechanics should be just the consequences of those assumptions. So the fact that we have a principle of stationary action is because we have all those four assumptions. And the fact that we have massive particles under scalar potential vector forces is a consequence of all those assumptions. The fact that we get relativistic mechanics is the fact that we are just trying to add the coordinate transformation. We don't even have kinematic equivalence technically for that. And the fact that we have a phase space and conjugate quantity can be derived by infinitesimal reducible and independence of the degree of freedom. And so this is kind of like one of the things that I care is that a lot of the people gravitate to interpretation of quantum mechanics and so on because we don't understand the quantum mechanics. What I realized like 7 years ago is I didn't understand classical mechanics either. I now think that I understand the classical mechanics. But if you asked me maybe 10 years ago, before I started thinking deeply about these things, I would have said, yeah, I understand classical mechanics. It just was only afterwards that I started really to ask myself, well, do I know what the principle of stationary action is? Why do I have conjugate quantities? Why do I have Hamilton's equation? Why do I have all these things? And it never even occurred to me that there could be answer to all those things, just because everybody around me would say, oh, yeah, it's like that, and that's it. And so there is a lot to understand with these things. There are probably better insights. And I do think that understanding classical mechanics gives you a lot of insights also then on quantum mechanics, because as I said, all these assumptions are going to be there except the infinitesimal reducibility. That's basically the only difference. And so if you understand what those other assumptions are doing, you're going to be understanding also what they do in quantum mechanics. And I think that's basically it. So if people are interested in learning more, and my voice is gone, we could set up an online reading group. If people are interested, we could have that reading group live streamed on the research channel, and we can find a time that works better internationally for people. And we could go through classical mechanics together, or we can also discuss, how all these things play in quantum mechanics and so on. And the only thing that I ask, if there is somebody, if somebody wants to do this, or if there are people that I want to do that, I'd like somebody to volunteer to organize that basically tells me what are the times that work better for everybody. They call the meeting, they prepare the thumbnails, stuff like that we need for you too. But again, if there are people that is interesting, I'd really like, as I said multiple times, I'd really like to build a community around this project, because there's too much for me by itself, and if we don't have limited resources of UMH, there's too much that needs to be sort of gone through. And so if we can create a sort of a global online community on this, I think, and we have the technology to do it. So. And again, to learn more is this, and that's basically it. So we'll open up to questions as long as my voice holds. I hope I have voice for tomorrow.
Right. So first question is from Xinyue. Can't we still have non-zero variation if we make an infinitesimal helix around the evolution path?
I don't think it would be a first order variation. I'd have to think about it. Good question. I don't have a good intuition. So so mathematically, the thing works, right? And so you're not going to be able to make a variation that catches flow. if you're making a helix, there are either two things. Either it's not a first order variation, so you can't do it, or even if you do it, the flow is going to be zero. I don't know which one is which. Very great question. You put me on the spot. Nice.
Okay, the next question is from Carlos. In 1 degree of freedom, you had to fix the gauge by choosing a particular theta2. Is it possible to choose other gauges?
Yes. And you might know that the Lagrangian is not uniquely defined by the system. And the way that you change the Lagrangian is by choosing a different gauge. And we have this in the book. There is like a standard gauge, like a standard a way to modify Lagrangian by taking a function and taking the gradient of it and doing funny things. And we show that that actually is just a change of gauge. And there are more transformations that you can do. And what it has to happen is that all the equivalence Lagrangian should be able to be reached by gauge change, which also tells me that all the gauge changes that we do in fields have to be connected somehow with these gauges of this vector potential. So in a sense, what we are saying is, in a sense that I don't know precisely how to make, but there should be a sense in which all the Lagrangian theories have to be gauge theories, because just by writing the Lagrangian, you are choosing a gauge.
Right, another question from Shinyue. Is there reason in this explanation that the Lagrangian has to be a function on position and velocity instead of position and momentum?
So it cannot be just a function. Oh, actually, no, it can be a function of position and momentum, now that I think about it. Huh. Okay, so the only way to say that the Lagrangian is a function of position and velocity and time without momentum is if you're able to write the momentum as a function of velocity. So that there is no other way. Like that's really the assumption, and you can show in many different ways that's always the same assumption. You could write the Lagrangian as a function of position, momentum, and time, because you can always write the velocity as a function of position, momentum, and time through Hamilton's equation. So in principle, you could always have a Lagrangian, it's a pseudo-Lagrangian. Let's call it pseudo-Lagrangian because Lagrangian has to be a function of position and momentum. So you can always write this pseudo-Lagrangian in position and momentum, but then you are always you have to work in phase space. Like it's explicit that you're working in phase space. But that you can do, yes.
Question from Daryl, or comment. To summarize the concept to make sure I get it. Given a flow in extended phase space and an arbitrary path, define the action as the path integral of the vector potential of the flow.
Yep.
A path with stationary action is equivalent to the path following the flow. It sounds kind of tautological and makes the principle of least action obvious.
Exactly. Yes, you perfectly understood. Yes. So what I say is the principle of least action is a very roundabout way to ask for the paths that are tangent to the flow. That's it. There's nothing mysterious about it. Yeah.
Assuming deterministic and reversible.
Yeah. Assuming deterministic and all the and independence of degree of freedom and all that. Yes.
So there are currently no more questions in the Q&A. There's a lot of enthusiasm in the chat for a reading group.
Yeah, so if you guys are interested, start sending me email, and then I'll put you on the Discord, and I'll create a channel in the Discord where you guys can figure out how to do it.
Chat, Daryl gives a shout out to the Mathemaniacs channel on YouTube, which explains the same concept presented here.
Yeah, he contacted me after he read the paper. There was a piece, somehow he missed the mathematical appendix where I explain everything in detail. And so he contacts me and says, oh, can you it doesn't seem so precise. What is not precise exactly? And I explain all of this in the appendix. Oh, there is an appendix. It's like in the introduction, I said there is an appendix for the map. That was funny. But yeah, so he contacted me and he did that. And he has something that I haven't, he has something more because he also links it a little bit to the Northern theorem, which I haven't done. So, okay, for example, that would be somebody wants to help there. There is something, there is a relationship. I have a conjecture on the Northern theorem through this interpretation that I'd like somebody to see if it works or not. So, you know, that there is a possibility. So the Legendre translation is more of a coincidence or it has a more mathematical, physical reason? I think it's more coincidence. So I don't have a way to fully understand geometrically what the Legendre is doing, except then, you know, to calculate that integral. So if there is a more physical reason, yeah, I don't know what it is. But again, the fact that I don't know what it is, it doesn't mean that there is none. The way that you would know if there is one, if you're able to represent some physical requirement more directly with the Legendre transformation. And maybe there is a way to do it, but I don't know that it is. But there is.
Question in the Q&A from Luke. Do you know to what extent the physical assumptions determine the cohomology of the space? Homology or cohomology?
I still, like, to me, homology and cohomology, rephrase it in a way that doesn't use the cohomology, because I get so confused by those mathematical words. I don't have a concrete intuition. Yeah, sorry. There's some mathematical terms that I still, you can put it in the chat. Like, there's still some mathematical term that I don't have a good physical understanding of them, and therefore I always forget the definition. So if you're asking me for that, I don't remember what it is. So if you can make it more explicit, what is it, the thing that you want me to comment on, I'll be happy to do that. This is basically why I started this whole project. Like, I can remember concept very well, but if they don't lock in some level of understanding and they're just mathematical symbols, after 5 minutes, they just go out of my brain. If I understand and I make a physical connection that it's meaningful and practical, then I can never remember it. I never forget it. Like, it's completely built in my brain.
Contact information in the chat. There's we have free time. Can we go to the skipped content?
Yes, we can certainly do that. So I can give you a choice. I have the sort of the more stuff on the relativity part, or I have the deriving the 3 dimensions, the fact that space is 3-dimensional. Is there any particular preference? So basically, right, those are the 2 things that I had.
Request for relativity in the chat.
All right, let's if everybody, somebody spoke up, so let's go to relativity. Okay, let's see, where do we go? Okay, let's see how the Hamiltonian extended phase space works, because I think it's very nice. So again, you have this Hamiltonian constraint that from your purpose works like a standard Hamiltonian. It's just that one of the variables is time. And so you're going to have a change of the time based on the affine parameters. You're going along the curve. the curve is not parameterized by time, it's parameterized by whatever parameter you chose. And so time is going to evolve on the curve. And that's going to be the derivative of Hamiltonian with respect to its conjugate. And its conjugate is minus e, right? So we're going to have to take this derivative in respect to minus e. So this part is 0, this part is 0. This is the only part that comes. The c, you can take it out. So you're going to have this minus e squared, but minus e squared is equal to minus outside and minus e squared. And so when you take the derivative, you get a minus here, this goes away, the 2 goes away, so you just have e over mc squared, which if you study relativity, you know that that's a special quantity already. Then you do the same thing with the position. Position with respect to a fine parameter, we are just taking the derivative with respect to p. And so here we basically have a p squared, because this is the only thing that we are deriving. And so we're going to have a 2, the 2 goes away, and so we just have the p over m. So we have e over mc squared, p over m, and there is no time dependence, and there is no position dependence, so these are all 0. And again, we know that there is for velocity, there exists a for velocity and for momentum. Now you can see that this is essentially the for momentum multiplied by m, right? And so we can take this c, put it down here, put the m on the other side, so we just have m dct over ds. And for this, we just have p equals m, the derivative of the position with respect to time. Well, we know what this is now. This is just the for velocity, because this is the for momentum. It's the for momentum times m, and this is the for velocity. Therefore, s here is proper time. So this Hamiltonian constraint has a conjugate, and the conjugate is proper time. So, and you can look at this. This is essentially, it's like a mass term. Like it's essentially p square over 2m, right? It's like it is a kinetic. It's like a kinetic term. So that's what it is, and I find it very nice that it just comes out. And as we already hinted, like this s is going to be proper time for particle, and it's going to be minus proper time for the antiparticles. Right, and again, if you then substitute the minus c, you can take the minus, put it in the energy, change the sign of the energy, and then change the sign of the proper time, and then you're gonna sort of make the particles antiparticle duality. So that's how it works. And again, it works very simply. It works a lot simpler than. And again, it's one of those things that I kind of rediscovered, and then I found it in the literature, and I kind of understand why this is not taught more. Okay, look, and that's fine. We can also correspond through email if you want for that question. Okay, so as I said, like this is in the standard way. This is what you do. You have the Hamiltonian. Now this is the true Hamiltonian. It's the conjugate of time. It's the generator of time. While this Hamiltonian constraint, in this case, is the generator of the fine parameter that happens to be proper time, right? This is how it's different. But if you do the calculations, you get the same thing. So if you do the velocity with respect to this Hamiltonian and do the calculation, you're going to have this pi over the square root of m squared plus pi squared over c squared. And since the energy is this, well, the energy is basically this rescaled. This square root is the same square root, except that we basically have removed the c squared from this square root, right, and it appear here, right? So what happens is you can think of dqi dt, this term, as being ds dt, how much the proper time changed with respect to t, the parameterization change in t, and then dq over ds. And this is invertible because time always has to be monotonic with respect to the parameterization. We can't go backwards in time or forwards. Like you always, like the path has to be, time still has to be a parameter. If you wanted to choose a time to be a parameter of the curve, we still need to be able to do it. and therefore the transformation between the affine parameter and time has always to be bijective. It has to be invertible. And this is where, you know, in relativity, we always think of time and space as kind of being interchangeable. They're not interchangeable. Word lines are the things that we want to describe. And word lines have to be curves such that time can always be a parameterization. All the time coordinates can be a parameterization of a word line, while spatial coordinates does not necessarily have to be a parameterization of the word line. And so if you do this and you get the equation from before, this ds dt is just the inverse of dt ds, which is just mc squared over e. And then this e was pi over m. The m goes away, you get a c squared here, and then you're able to get that right away. Okay, so it's nice because everything it sort of fits, but if you make this break, you can actually understand more about the geometrical structure and what is actually going on. So much so that then you can understand how the standard Hamiltonian is embedded in the Hamiltonian constraint. So if we have valid states, the Hamiltonian constraint always have to be 0, because that's a constraint. It's if you take this 8-dimensional space spanned by time, position, energy, and momentum, right? There's going to be a constraint, so you take a 7-dimensional subsurface of it, right? And so you are on that surface, and so h is equal to 0, but also that is going to give you the constraint between the energy and the Hamiltonian. So both of these have to be true. And now we can, since this has to be 0, and this has to be true, h minus e has to be 0. So let's stick a constant between the two and assume that for now that this has no dependence. Then if this is equal to 0, this is equal to 0. So the Hamiltonian constraint becomes the expression of the energy with respect to the Hamiltonian. And since you have E equal h, now you can go and write the equation on either the extended phase space and recover the equation on the standard phase space as basically as part of this constraint. So the derivative between time and time is of course equal to 1, and since we have invertible, we have that the derivative in s with respect to p is times ds dt is going to be equal to 1. Using the Hamiltonian on the extended phase space, this is the derivative of Hamiltonian with respect to minus e, but this here is lambda, because this does not depend on e. This is the only e dependence, and so you have minus c times lambda, therefore you just get a lambda. And this for dt ds times lambda is equal to 1. So this lambda here is just the inverse of ds dt. So it's basically, this is dt ds. This is telling you how fast the parameterization goes with respect to time. So again, it's a physical quantity. It's not just something meaningless. It has meaning. And then if you do the same trick, you can express dqi dt. You do the same trick of putting the s here, and then you do your derivatives and so on. You're going to recover the standard equation of Hamiltonian mechanics. So the picture of saying I have a Hamiltonian constraint, or I have some Hamiltonian that it's with the square root of a lot more complex, are the same. You can go from one to the other. And again, I like when all the bits of math like that work well. Even more, what's going to happen when you have sort of particle-antiparticles? You have different terms in the Hamiltonian that if you are on this constraint, this function is a lambda, and if you are on this constraint, then this function is a lambda. Right? This is the thing that it's interesting to me. So now that we have particle-antiparticles, you can see that because we had the e square, we can turn that Hamiltonian constraint into actually two constraints with respect to the Hamiltonian. So we're going to have e minus h1, and this is h1, and a E minus H2. This is H2, and each one is going to be minus H2 because we had to stick a minus sign here to make it work. And so when you do your derivative in time, right, the lambda that you have in front of this is no longer, which would be this, right? It's no longer independent of E. It is dependent of E. So it gives you some contribution to the flow of time with respect to the parametrization. And that's how you get this 2 to disappear. Otherwise, you wouldn't get it. So it's interesting to me how all these pieces work. And again, there might be, for now, this is just sort of understanding how the mathematical machinery works, which I still think is interesting, but I don't know if there is more than that. And there probably isn't because, again, there is a choice of the parametrization. We could change the parametrization and change the Hamiltonian, and then the Hamiltonian constraint would be different. So then the other thing that you can do in this formula is to make this quantum classical parallel. So we saw that there were this idea of particles, antiparticles, but one of the things that you can note, like this is the Hamiltonian constraint. And now if you've done quantum field theory, this really looks like the Klein-Gordon equation. So we have a momentum operator square here, and this is the nabla. And we have an energy operator square here. This is the derivative in time. And then we have a mass term, and the mass term is here. Like the only thing that you have an H bar here, but again, instead of thinking it here, think of these H bar as part of these operators because they're part of the energy and momentum operator. Then it suddenly makes a lot more sense. And these minus signs with respect to this, it's because there is an I square of the operator, right? So this H bar shouldn't be here. You should have an I H bar partial in time all square, and then we will get the sign to actually be exactly the same. And so, again, what is the Klein-Gordon? What is the Klein-Gordon in quantum mechanics? Is just the Hamiltonian constraint of classical mechanics. And the same thing, I think I have it later, it works for the Dirac equation. Another thing that it's nice is that you see how you have the Hamiltonian constraint times the wave function. You can do the same thing in classical mechanics with a probability distribution. Because if I have a Hamiltonian constraint and I have a probability distribution, then either I am over a physical state, and therefore the Hamiltonian constraint has to be 0, or I'm not in a physical state, then the probability distribution has to be 0. And so this constraint of Hamiltonian constraints times the probability distribution equal to 0, this has to work in the same way, both in classical mechanics and quantum mechanics. Again, right now, this is at a level of analogy, but I can't imagine that this can't be, we have a more formal theory that it's sort of abstract, and these are just two instantiations of the same idea in both. So ideally, what I'd like to have, and we'll talk about it when we do physical mathematics, I'd like to have a Hamiltonian theory defined on a generic notion of states and processes, right? But then in the classical case, it's implemented in one way, in the quantum case, implemented in another way. And again, there's so many similarities that I can't imagine that this cannot be done. Another thing that, again, connects to gauge theories, this is the Hamiltonian constraint for charged particles. So this is your field. This is the vector potential, right? And this is your charged particle. This Q is the charged particle. And what you find is that M lower U, right, which is essentially the kinetic momentum in covariant components instead of contravariant components, is P alpha minus Q A. So basically, this term over here is just a for velocity term, right? You have 1/2 M U contracted with U, so this is a normal view, plus 1/2 MC squared. This is the Hamiltonian constraint. This is equal to 0. And so the only thing that this Hamiltonian constraint is saying is that the norm of the form velocity has to be 0, which I find it completely hilarious because it's basically telling us nothing. And then you have the fact that the real physics is hidden in the fact that the form momentum here is not just the conjugate momentum, the kinetic momentum is not just the momentum, but there's this extra term. And this is where all the physics is, like this term here is all the physics. And the thing that is interesting, I'm thinking about gauge, this part, mu alpha, has to be a gauge invariant term. It's the thing that we measure. Conjugate momentum, we don't measure. And the for potential is also like defined up to a gauge. And so the gauges of these two have to be in such a way that when they subtract, you get something that it's gauge invariant, right? So this thing is gauge invariant. These two things are not. Now, again, we can compare to the Klein-Gordon equation of a charged particle. And again, you see that there is this term partial derivative minus IQA. And again, this is called the gauge covariant derivative. And again, we're missing an IH bar here. And so that would make this also I go away. But what would happen is that this corresponds to this corresponds to this. So this gauge covariant derivative is just the conjugate momentum. So when we're writing this Klein-Gordon equation, what we are actually writing is that the norm of the form momentum has to be equal to C. That's all what we're saying. And again, there's so many things that become, like as we pointed out for the action principle, it became like this tautology that you're basically trying to look for the simple thing. Also, this becomes like this. And 10 years ago, I didn't know that this could become like this. And if we keep going and look for simpler explanation, that's the only way that we can actually find them. And again, I understood this, not because I was looking at quantum field theory, but because I was trying to better understand the classical mechanics and its relationship to relativity. So again, the idea that if you want to understand physics perfectly, you just have to go and look at the most complicated theory possible, quantum field theory, because that has all the answer, because that gives us the best description of nature. It doesn't work. You go to the simplest theory, fully understand the simplest theory, and then you go to the more complicated one. Once you fully understand that, once you've completely exhausted all the possible insights that you could get. So this is why I had this this relativistic part and the connection to quantum field theory to sort of hopefully give you that sense. And that's basically it.
All right. At the end of the hour. So I think this is going to be a good place to stop. Mm-hmm. Thank everyone again for attending today. And we will have the third and fourth lecture at the same time tomorrow.